way to do this. All right, so we're working with these long, skinny trapezoids. Matt asked a good question of like, well, are we always going to use this rule, or are we sometimes going to use rectangles? So the one thing about trapezoids is while they are better at approximating, usually to make a better approximation, we're going to lose some of the ease of making the approximation. So while rectangles don't do as good of a job, they have a much easier area formula. The area is just base times height. Does anyone remember the area of a trapezoid from geometry? Probably not. It's not that much more complicated, but it will be a slight bit more complicated. And what? So you could do a rectangle and a triangle. That gets a little bit hard because we're going to be doing like 6 trapezoids. So we're going to want an area formula in general. It really is just going to average the 2 heights of the things. So I'm going to give you that area formula, but just know that because we're getting a better approximation, we have to give a little bit to get that. So we're kind of giving up the easiest area formula we can remember to something that's a little bit harder, but not too bad. Yes, we will have to remember it. So the area of a trapezoid, I'm going to give you a couple of ways to remember it. This is how it's normally written in textbooks. 1/2 height, base 1 plus base 2. I'm going to label where those things are. The bases, normally we think of trapezoids kind of rotated, so their parallel sides are the bases. So this would be our base 1, and this would be our base 2. So you're talking the 2 y values here. So just like the y values we would have done in Riemann sums, we're talking like those 2 bases, those 2 y values will be my base 1, base 2. And the height is going to be kind of right here. The height would be like that delta x we talked about last time, the kind of distance along the x-axis. That's going to be the same thing there. So if we're writing this in terms of like how we wrote it last class, I would have my 1/2, my delta x, that's your little thing along the x-axis. And then the next way to write this is a little bit weird. So I'm just going to write it kind of weirdly. Let's just call it y sub 1 plus y sub 2. So we're going to get 2 successive y values going on. Now, if you're wondering where this formula comes from, there's actually a different way to write it if you are a little bit loose with how you write your fractions. So your height is the same thing as last time, but these bases are really just being averaged here. So that triangle kind of makes me have to average the 2 heights to even them out. So I always write the 1/2 out front just because that's how I learned it. But if you want to write it this way on the left-hand side, essentially what you're doing is finding like a perfect height of these 2, cutting it in half, and finding the area of that rectangle. So kind of taking this part and adding it down here. Yeah, so it's the same idea, and we'll use this in a second, so it'll make more sense once we start using it. But you can kind of set it up either way. So if you were working with the one on the bottom, you would want to do your delta x just like we did before, kind of the distance along that x-axis, and then you're going to average your 2 y values. Do you guys, which way do you prefer to write this? The averaging or the 1/2 out front, or you don't really care? This one? The first guy I wrote? You like the one on the wall? All right, I'll mix it up. It doesn't really matter. This one on the right-hand side gets used a lot in textbooks, I think, because some people like to factor that 1/2 out in front of everything. But whichever way works for you, I'll do a couple of problems different ways so you can kind of see what works. So we're going to get the hard one out of the way first, and then we'll take a break after we kind of talk about over and under approximations as well. This is the one where we made our own table instead of getting provided a table. So we'll do the hard one up front, and then we'll come back and we'll look at those AP style questions, which are actually even a little bit easier. Also, just for giggles, let's learn a couple new values of sine of x, because we know one of them pretty well, but I would like to learn more of them. Yeah, do you guys still remember sine of 0? It is 0. All right, so we're going to graph sine of x we're going to find a few values. This n equals 4 is going to tell me how many trapezoids we're going to do. Just like the kind of sub intervals talked about the number of rectangles. So we're trying to go from 0 to pi on our x-axis. And we are going to try to find the area under sine of x. Has anyone graphed sine of x recently? Thought about the graph of sine of x? It's one of the wiggly boys, yeah. Do you know where that one starts on the y-axis? What's sine of 0? 0. So notice how it goes through 0, 0. It's like the graphs means something. I think we as teachers do a really bad job of explaining that they're kind of different representations of the same thing. So we're going to go from here to here. So you see this little like camel hump right there where my cursor is? That is what we are trying to find, the kind of area of that guy. So let's roll. So I want to draw a little picture of that. So there's 0 and there's pi. So I want to make it from 0 to pi in 4 steps. What should I count by? 1/4 of pi, or pi over 4. So a way you can do that, if you're not as quick thinking with fractions as Derek was right there, you can take your end minus your beginning, so pi minus 0, and divide it by the number of shapes you're using. So I would get pi over 4. So let's count by pi over 4s, and then we're going to find our sine x values. Oh, that was you. No. Oh, cool. That's very calming music. All right, 0, pi over 4. All right, the next one would be pi over 4 plus pi over 4, which is pi over 2. I'm simplifying my fractions. You're not wrong. All right. I have 2 pi over 4 that Derek said and I simplified. We're adding another one, so 3 pi over 4. And then what's the last one? Pi. All right. Notice we took 4 steps and we made it from start to end. All right. What did we say sine of 0 was again? 0. Do you think you know any other values based on the graph I drew right here? Does anyone think they know what sine of pi is? 0. It's another x-intercept. Does anyone think they know where this point is? How low and how high do sine get? 1 and -1. So this pi over 2 is 1. Now the secret values, that would be great, wouldn't it? It's not 0.5. It's a number that you may have heard before, and they're the same number. Square root of 2 over 2. It is obnoxious. So all of the pi over 4s are going to be square root of 2 over 2 plus or minus for all of sine and cosine, actually. If it's ever some pi over 4, you're either going to get positive or negative square root of 2 over 2. The unit circle. So we're just going to focus on these ones right here for now. All right, so we have our values right now, and we are going to try to set up our 4 trapezoids. So I'm just going to draw a little bit of a picture so we can reference as we go. I noticed that everyone who started drawing pictures on their notes checks for the Riemann sums ones seemed to be pretty helpful, helped us visualize a little bit. So let's draw out these trapezoids. So our first trapezoid is actually kind of silly trapezoid. It is a triangle, and that's because one of our bases is 0. So our first trapezoid, we are going to do 1/2. So I'm going to write it this way first, the way I wrote down first, with the 1/2 out front. I'm going to do my delta x. So I want to know how far along the x-axis is this distance. How far to get from 0 to pi over 4. Pi over 4. Not crazy. Now, the kind of cool thing about trapezoidal rule is since we use both bases in our formula, unlike Riemann sums where we had to choose one of the two, we're actually just going to add them together. So I'm doing 0 plus root 2 over 2. That's from our area formula for trapezoids. So for trapezoidal rule, it'll always be there. You could alternatively, if you were liking the other way I wrote this, you are averaging these two. So that's where the over 2 comes from. So either way you write this, either one is fine as we go. If you notice, that trapezoid right there, I'll use air quotes, is technically a triangle instead because of that 0. Anyone remember the area formula for a triangle? 1/2 base times height. So instead of the height being this, it's our base, and we just have that 1 height. So you can now tell everyone a triangle is just a stupid trapezoid. It is, but since we have this 0. Yeah, they just didn't want to make it that long. All right, let's do the next one. So we could either put the 1/2 out front, or we can divide our addition of bases by 2. What is our next delta x? We're going this distance right here, or how far to get from pi over 4 to, yeah, it's still going to be pi over 4. Actually, will that change for any of these guys? No, we made it so they were equidistant along the x-axis. What 2 values will I be adding inside here? Perfect. Now, in some textbooks, you'll see an interesting formula where they have 2 times some of the bases here. And that's because a lot of these will show up twice, except the first and the last one, really. So you can do some cool simplifying if you factor stuff out. I don't like to factor stuff out because I like to see my 4 trapezoids at the end of this. All right, what's a color that'll go nice with what I've got so far? I was thinking the same thing. All right. In sync today. No. All right. What do we think it's going to look like? 1/2. Careful. How long along the x-axis is that one? It's still just pi over 4. So these distances along the bottom, you want to think from pi over 2 to 3 pi over 4, we only went up pi over 4. All right. 1 plus the square root of 2 over 2. Now, if you notice, the yellow trapezoid and the green trapezoid should be the same size. On our picture, they are. Notice in our area formula, the only difference is I switched the order of the addition, so they are the same size in general. All right, and then what's our last one going to look like? All right, so like the first one, but just flip the addition. It is. Do you know today's date is a palindrome? It's also called, what was it called? An ambigram. I saw it on Facebook this morning, where like you can read it upside down the same way. New words, apparently. If you write the 2's like clock 2's. Like this guy. Okay. Yeah. You know, a lot of teachers. Oh, I just wrote this the same way and I didn't mean to. You know, a lot of teachers can read upside down just because. All right, so there we go. That's basically it. So you kind of gain something, I think, from the adding the bases. You don't have as many decisions to make as you did. What the heck is happening in the hallway today? Oh, that's fair. So you gain a little bit by being able to not have to choose one of the bases here. You just get to add them together. So you kind of got a harder area formula, but it does make some of the decisions easier. What? Yeah, so we would have to add all of this up. We could plug it into a calculator. Honestly, on the AP test, if this is a free response, we can leave it exactly like this and not simplify it at all. which is a really cool, nice way. Even if I had units, I could just be like units squared on the end. All right, so before we take a break, one more thing. I want to know when it's an over or under approximation. What do you think has to do with this? What's the difference between these two pictures if you had to use calculus words? This guy is concave up like a cup. This is concave down like a frown. So concavity is actually going to give us our difference here. I'm going to kind of exaggerate it a little bit by drawing some trapezoids underneath. So let me make a bigger one so it's easier to see. What? Yeah, you can make them any distance you want, but they should be between your curve and your x-axis. So I'm imagining my x-axis is underneath. Does that set of trapezoids look like it is under or over approximating the area? Yeah, you got this like extra stuff in here. So this would produce an over approximation. You could draw something similar here. The bigger you draw the trapezoids, the easier it is to see. So this is just an example. Or kind of the greater the concavity, the easier it is to see. But you can see here, you're kind of missing out on some of that area. So this would be an under approximation. This happens sometimes on the free response section of the AP test. You'll see them ask you to write one of these trapezoidal rule sums, and then they'll ask if it's an over or under approximation. So we're going to take a solid break. When we come back, we're going to set up some actual AP test question ones, and we're going to talk a little tiny bit about position, velocity, acceleration with my dog. So you don't have to. The over-under gets a little bit weird at that point if you're counting things as negative, but you can do it underneath. You would just be bound on top by the x-axis, kind of go down, and the pointy part would go down as well. All right, let me make this smaller. We don't need 15 minutes. Yes. Actually, I feel like my back to me. I'm sorry. Celebrate. Did anyone else feel like an instant mood change? I got to school this morning and I was like, I'm actually happy to be here. Feels good. Oh, let me grade some quizzes. Whose was I grading? I can't remember. Oh yeah, is everyone ready for spring sports? Or are you just extending your track season?
Yeah, it's on Monday, but it's like the next sport.
Yeah. Do you just jump or you're running as well, right?
I mostly jump. I don't like running, but my coach will call 4x4 or the 4x2. Or like
You guys do hurdles?
I did hurdles.
You know who the hurdles coach is?
Yeah, I did hurdles. I didn't like them, so I stopped.
No one likes hurdles. He does. He does. Nate Griven's older brother did. That's about it.
Austin's really good at that.
Yeah, I have him in BC. He reminds me so much of a kid I used to teach here who did hurdles for Chris for 4 years. They even have the same handwriting. It's really creepy. Very similar vibes. So excited to be track mom this year. I'm just gonna buy like 100 Clementines.
Please do. That'd be so fun.
I got permission yesterday. I was like, can I do that? And he's like, I don't know the COVID guidelines. I was like, no, just like sports wise, is giving the Clementine okay?
I want to play a big box. Like some juice boxes.
Yes.
I've never used Apple.
Do we only wait? Oh shoot! It's 105.
I don't like them.
No. Advisory was silly this morning because I only had a senior in my 5th block, so it's like we're supposed to talk about scheduling. I'm not gonna do that. All right, so let's transition to the questions where we're already given the table. Do you guys want to draw a picture for this one, or are you thinking we can do it without the picture? Whoa. All right, so let's try to do this without the picture. Anyone kind of develop a preference for which way they like to write this formula, looking at this one? Top one, bottom one? Okay, the top? All right. Yeah, so as long as you remember that 1/2, it's fine to put out in front. You could also factor that 1/2 out if you would like to. Just be careful about factoring out the delta x here, that pi over 4 in this case. It would have worked for this question, but in most of our table questions, which is the ones you're really going to see on the AP test, a lot of times that delta x is not the same for every sub-interval, so you're going to want to make sure that it is before you factor something out. So let's look at this guy. We've got a table. It's f of x. It's a continuous function. Cool. One of the most important words in this question, 4. We want 4 equal subintervals. So whether you draw a graph, one thing I like to do, and I think I did this last time, is kind of block out where my trapezoids would be. So you'll usually see me kind of do those subinterval lines there. We're looking for a trapezoidal approximation. So you're going to see this word if they want you to use trapezoid. So kind of the benefit of Riemann and this, they're kind of in your face about what they want to do. Question, is the delta x, and when I say that, I mean the little distance along the x-axis, is that going to be constant for all of my trapezoids, or is it going to be different? It's constant, right? How big is that delta x every single time? 0.5. If you want to, I know last class I was kind of writing them up here. You can write that down so you're not tempted to use the successive x values if you want. But here we go. We've got 4 of them. First one, 1/2. Why? Because it's 1/2 all the time for trapezoids. I don't like the way I'm writing those twos. 0.5 is our delta x. And then what else do we need to put in here? Ooh, I like the idea of adding. Let's add those y values. 3 plus 3. So you're going to have 1/2. This is for your x's, your delta x. These are going to be your y's. Those are your y values. So if you're drawing your picture, those are your 2 heights. And then your, so this is your 3, 1/2. Also, that one would be a rectangle. Notice you're averaging 3 and 3. It's a rectangle on the top.
But like the actual graph.
We don't know what the graph is because it could be doing whatever the heck it wants between 0 and 0.5. All we know is that at x equals 0 and x equals 0.5, it's at the same height. So it could be doing this, could be doing this. We don't know. All right, let's do the next one. Will it have a 1/2? Will it have a 0.5? All right, what comes next? 3 plus 5. All right, next one. How does it start? Actually, just give me the whole thing. 1/2, great. And a 0.5. Any more guesses? 5 plus 8. These are so close to Fibonacci numbers. Because the 5, 8, 13 is. And the 3, 5, 8, 13. It's all Fibonacci. What's the last one look like? 1/2, 0.5, 8 plus 13. Now, this is an actual AP test question. I'm going to tell you it was non-calculator. So, how could I simplify this? Well, what do they, yeah, Derek, what's your idea? Good. So I like the idea of taking this and making it a little bit simpler. Also, do you guys notice that it's in every single term? Yeah. So let's factor it out. So we got 1/4 out front from the 1/2 times the 0.5. Then I'm going to add these together. So I have 6, 8, 13, 21. All right, that's all the math I'm doing. Find me an answer. Twenty-one, 40. Did you guys get 12? Yeah. Sick. All right, let's start to lay some words over. So last class we talked about going from a rate of change back to not a rate of change. So we were talking about, what was it, like liquids moving around? So we had some coffee. We're going from like ounces per minute times some minutes, and we could get ounces as our final answer. So one thing you're going to notice is we're going to come back into the world of position, velocity, acceleration. With derivatives, we could take the rate of change of position was velocity, rate of change of velocity was acceleration. Well, now this is giving us a way to at least approximate the way back up. So if you think of what we're about to do, we're about to take meters per minute and multiply it by minutes. That'll cancel our minutes and we'll get meters, some distance units. So that's pretty darn cool. Do you guys want to try this one on your own? Do you think you can do it? Yeah. All right. One thing to be careful of before you get started, you are doing 3 sub-intervals, but when I go to block this out, there's 4. So what's wrong? Can anyone figure out what's wrong? I have to start at 2. So there is some extraneous information here. So you're not going to use this guy at all. So set me up your 3 sub-intervals. If you can, find me a number. If you have a calculator with you, you're more than welcome to use that. Something's going to be weird about that answer, considering that the unit is meters. I want you to figure out what you think that means.
And these are still, they can be done packaged. So in this one, we could, like, where we factored out that 1/4 for the 1.5, we could. Yes.
Again, it would be nice if you could find a final answer. There's going to be something slightly strange about it, considering the unit is meters. See if you think you know how to remedy that in your noggin. All right, since I see a lot of people moving to calculator stage, I'm going to start setting up. This time I'm going to move the 1/2 inside just to give you guys the other view of that. Oh, they tried to fool you. The first 2 or 3. So that's the 1/2. Yeah, so it's just 2 different ways to write it. Honestly,
would it be better to use the 1/2 one for when it's always?
it really doesn't matter for the 1/2. I'm just giving you a couple of ways. Honestly, I kind of wish I got taught this way because I think it gives a better mathematical interpretation of what you're doing because you're essentially averaging those 2 heights to get your like average height. So mathematically, I think it makes more sense. The 1/2 is a little bit easier if you can factor stuff out. So just alternatives. Did you guys see how they were sneaky and they made your last delta x different? How sneaky. Did you guys give me a number?
-450.
What? -450? I can't fool you. Too many of you take physics. All right, so yeah, so what does this 450 mean? It means that our train was it going backwards the whole time? Yeah. Does your setup look just like mine? Okay, but you have 100 plus 40, 40 minus 120, negative 120 minus 150? Do you have your 3, 3, 4, your delta x's? There we go. All right, so let's pause. So what this means, you guys did notice this train wasn't going backwards the whole time. When does it look like it turned around? Somewhere between 5 and 8, it turned around. Wherever that velocity would have been equal to 0. It might have turned around more in the middle. We're not really sure. But it looks like if it turned around once, it was going to be between 5 and 8. But it looks like it was zooming pretty fast backwards towards the end of this time interval, which is why we're ending up behind our starting point. So whatever we did, we're ending up 450 meters kind of behind our start. We'll usually get more information about direction if they want us to be kind of more specific there. So sometimes they'll give you an east-west and tell you which one of those is positive. But we can kind of see as we go, we can get a little bit more information about PDA. So what I want to do is I want to take one table and answer a few questions and kind of review Riemann a little bit. So we're going to do a little bit of position investigation with my dog, Bo. We're going to skip that lake question. So my dog is running back and forth along a single line. He's very fast when he decides to run. He puts his butt down and his arms out. He just goes. So we've got his velocity measured in meters per second, time in seconds. He's running around for about 1.5 minutes. So we're going to do a left Riemann sum to find the distance he traveled between 0 and 60 seconds. And then we're going to find his displacement with a midpoint and do a little bit of talking at the end. We do need to talk about the difference between these two words. Have we talked about them yet? Distance and displacement? No? Yes? Maybe? Good. So track starting days. Let's use a track metaphor. If you're talking total distance, let's say you run a 400, which is once around the track. Your total distance traveled is that 400 meters. What would be your displacement? 0. You're ending at your starting point. That means we need to treat things a little bit differently. So let's talk about total distance. We need to count everything as positive movement because we want to make sure we don't cancel anything out. So let's look at our 4 subintervals. We're going from 0 to 60. So let's see if these 15s work. 1, 2, 3, 4. Perfect. I could also do that by doing 60 minus 0 all over 4 to get that 15, but it looks like the subintervals in the table work. Are those going to be consistent delta x's? If I wanted to factor them out, could I? Yeah. All right. What's the probably most important word in this question as far as what I'm going to do now? Left. 4, also helpful. A number, though. All right. No. So notice, yeah, that's actually probably the first word. Here we're noticing Riemann. Riemann means rectangles for us. So let's look at our first rectangle, which is right in here. What is the base of that rectangle? So if I envision this along the x-axis, how long would it be? 15. All right. So think of like a delta t in this case. How far from here to here? How tall would he be if we are talking a left Riemann sum? 1. We want the number on the left. I like when they give us the tables horizontally notated because that works better. All right, let's look at the next rectangle. So we're not from 0 to 15 anymore. We're going from 15 to 30. So how far along the t-axis, if you will? 15 times 6. That's how tall. All right, let's keep transitioning. Now we're going 30 to 45. Still 15? Times 9. Perfect. All right. I got one more. What does it look like? 15 times 5. All right. Now, notice what y value did we not use for our 4? We didn't use 2. That's the rightmost one. We used a left Riemann sum. Can I be our calculator, or do you guys want to calculate? I can do it. 315 meters. I'm a magician. I could also do 15 times, let's see, 1 plus 9 is 10 times 21. Which is, yeah, 300 plus 15. That works.
Is that like all the work you have to do for it?
Yeah, so that is all the work we have to do. I really like Riemann sums. When I see them on the AP test, I always get really happy because I'm confident we're all going to get those points. Now, the distance meters here makes sense, and we would want to make sure we could check that. So remember that this guy was a time in seconds, and this was a speed in meters per second. Now, this is total distance because I counted all of my velocities as positive. All right, let's find my dude's displacement with a midpoint Riemann sum. All right, I would like you to talk to your neighbors. I'm going to kind of erase my work right here. I now want to go from 0 seconds to 90 seconds with 3 sub-intervals. How long is each of my intervals? All right, if I want to go in 3 steps, that means my steps need to look like this. Now, why is that convenient if I'm looking for midpoint sums? Yeah, I noticed that I actually do have a value in the middle. If I didn't, I would be in trouble. You would have to find a different way to set this problem up. So that would be a good approximation. You're always going to get one if they ask you to do a midpoint Riemann sum. We're not guaranteed. That would work if our function was linear. Averaging them, we're not guaranteed a linear function. So that would be a good way if I didn't have any other options. But we'll always be able to find a middle. All right, what's my first rectangle going to look like here? Good. 30 is my delta x. Now 6 is my middle value. All right, someone whose name is not Matt. What's the next one look like? Okay, 30 times. Good. So still 30, going from 30 to 60, middle value 5. All right, someone whose name is not Matt or Herbie. 30.
Oh, there she is. Go.
Wait, actually? I don't know. All right, is it okay? Is this -3 okay? Am I allowed to count my guy going backwards? All right, he is going. I am. I'm finding displacement. If we're looking for displacement, it is okay for us to cancel out some of that distance. If this had been instead total distance, I would have wanted to count that as +3, so I can accumulate all of that distance there. All right, if I'm looking at this guy, this is 240. What are my units? Meters. We're still taking meters per second and multiplying it by meters.
If we were doing distance, we would change it to a positive.
Yes. I have 2 minutes to do this last problem. All right, we're going to do the same thing with this 3 sub intervals at the very end here. Yeah, but we're not going to get to it because I am not good at time management today. Mm-hmm. Yep. Nope. We're going to do one different thing right here. All right, this last one, we're going from, yeah. So here we're going to go from 45 to 90. We got 3 sub intervals. Here we're going to use the 1/2 because we saw the word trapezoid, and we're going to do one different thing because we see total distance. Sorry, I can't get the table in with what I'm looking at. We're just going to do this one, and we're going to finish here. So each of these will have the 1/2. Now, all of my sub intervals, 45 to 60, 60 to 75, 75 to 90. Do you agree they're all 15 long? All right, notice in the first one, we've got velocities of 5 plus 2. Great, easy. Next one gets a little funkier. We have 2 and -3. We don't want to cancel out any distance because we say total distance. So what's this going to look like? We do. We're going to do 2 plus 3. This one said total distance here. So the answer to that is no. Yeah. You're essentially absolute valuing. All right, the last guy here, we're going to do not -3 and -5. We don't want to cancel out a distance. 3 plus 5. Which equals 150 meters. So the first one we did is technically distance and displacement here because all of the velocities were positive. So it didn't matter either way. So we'll only have to pay attention when they're negative. All right, we have about 30 seconds before we leave. I will tell you guys, quizzes will be graded next time, and we'll start out by correcting Riemann notes checks and doing the notes check on this before we take a foray into finding anti-derivatives. It's just everything backwards. It's not bad. Yes, shoot me an email and I'll make sure that I get it where it needs to go. Thank you, ma'am.